Hello and welcome back for some more reinforced concrete design. In this session, we're going to start talking about columns, and namely how a section can be influenced by both axial and bending actions. Axial load can be compressive or tensile. Usually, the axial load in a column is compressive, as shown in this slide. The presence of axial forces results in a shift of the position of the neutral axis. The stress distribution in the cross-section becomes non-symmetric. Eurocode 2 assumes that a reinforced concrete section subjected to a moment M and a compressive axial load N can be in one of the two ultimate limit states. State 1 represents the section under compression and tension, where the limiting compression strain equals the ultimate value of 0.0035. State 2 represents the section under compression only, and in this case the limiting compression strain is 0.002 at the level of 3/7 of the section depth. Here you can see the distributions of strain and the corresponding design stress in a reinforced concrete section in the two states considered. Note that the rectangular stress block method was used to represent the stress distribution. In state 1, the neutral axis passes within the section and a large part of the section is in compression. This represents a situation where the moment has a larger effect on the section than the axial force. In state 2, the neutral axis passes outside of the section and the entire section is in compression. This represents a situation where the axial force has a larger effect on the section than the moment. In state 1, the compressive strain at the top of the reinforcement and the tensile strain in the bottom steel have the expressions given here. These were derived from the similarities of three triangles in the strain distribution in the reinforced concrete section. In state 2, the compressive strains in the top and bottom reinforcement have the expressions given here on this slide. These expressions were also derived from geometrical considerations of the strain distribution in the reinforced concrete section. The resistance of a reinforced concrete section subjected to bending and axial load consists of the three following forces. FCC is the compressive force developed in the concrete and acting through the centroid of the stress block. FSC is the compressive force in the top reinforcement and acts through its centroid of the reinforcement area, AS tag. FS is the compressive or tensile force in the bottom reinforcement, and it acts through the centroid of the reinforcement area, AS. Given the absence of vertical forces, we can write only two equilibrium conditions for a planar system of forces, FCC, FSC, and FS. The sum of forces in the horizontal direction yields the axial resistance of the section, where the force Fs can be detracted from the sum of SCC and FSC in state 1 and added to it in state 2. Substituting the maximum values for FCC, FSC, and Fs results in the following expression, where lowercase fsc is the compressive stress in the top reinforcement area AS tag, and lowercase fs is the compressive or tensile stress in the bottom reinforcement area AS. The moment resistance of the reinforced concrete section can be found from the sum of moments generated by the three forces. Taking the sum of moments around the mid-depth of the section yields the following expression for the moment resistance of the reinforced concrete section. Note that the moment produced by the force Fs can be added or detracted depending on the design state considered. Substituting the maximum values of FCC, FSC, and Fs results in the following expression. In state 1, the expression for the moment resistance of the section takes the following form. Here, the moment produced by the force Fs is added to the sum of moments produced by the forces FCC and FSC. In state 2, the entire height of the section is in compression, and the height of the compression stress block, S, equals to the height of the section H. As a result, the lever arm of the force FCC equals 0, and the effect of this force on the moment resistance of the reinforced concrete section is eliminated. Additionally, the moment produced by the force Fs is detracted from the moment produced by the force FSC. Because the direction of moment acting on a reinforced concrete column can be reversed, for example due to changes in loading conditions, steel reinforcement is usually arranged symmetrically in the column cross-section. In this case, the area of the top reinforcement AS tag equals to the area of bottom reinforcement AS. The expressions for the axial and moment resistance of the section can be rearranged in the following way, where stresses in the compressive and tensile reinforcement depend on the location of the neutral axis. A direct solution of the two equations above is very tedious. Therefore, design charts are used instead for symmetric sections. These design charts are based on non-dimensional ratios depending on the axial force and moment applied, on section geometry and dimensions, as well as on concrete and steel strengths, and the ratio between effective and actual height of the section. The charts allow us to obtain reinforcement ratios for the reinforced concrete sections subjected to certain loading conditions. Here you can see a typical chart that can be used for the design of a rectangular reinforced concrete section with the D to H ratio equaling 0.9. Note that the curves you see in the chart are called interaction diagrams. Here you can see a typical chart that can be used for the design of a circular reinforced concrete section with a depth D over H ratio equaling 0.6. The axial forces are usually applied eccentrically on columns because of non-symmetric loading arrangements and structural imperfections. We consider the axial force N applied at a distance E from the section centroid. Let's move the force to the section centroid. To keep the effect this force has on the section unaltered, we should add a moment equaling to N times E. Note that the moment rotates the section in the same direction that the force applied at the original position would rotate around the centroid. Additionally, the eccentricity E affects the position of the neutral axis in the section and hence the stress and strain in reinforcement in concrete. In the ultimate limit state of a reinforced concrete section subjected to an axial force N and a moment M, each eccentricity E corresponds to a unique pair of the axial force and moment. As a result, a unique curve can be built. This curve is called an interaction diagram and represents a failure envelope. The area within this curve represents all loading combinations satisfying the ultimate limit state conditions, while the area outside of the curve represents loading combinations leading to failure at the ultimate limit state. A typical interaction diagram can be seen on this slide. As you can see, this diagram is divided into two ranges, representing the tension failure and compression failure. The radial lines in the interaction diagram represent loading situations with linearly increasing M and N and constant eccentricity. The tension failure of a reinforced concrete section represents the loading combinations dominated by large moments and associated with large eccentricities and small depths of concrete in compression. The point of intersection of the interaction diagram with the M-axis represents the case of pure flexural failure. The tension failure of the reinforced concrete section begins with the yielding of tensile reinforcement and is followed by the crushing of concrete. The tension failure and compression failure ranges are connected at the point representing a balanced failure. This is the point where the tension steel yields simultaneously with the crushing of concrete. In the balanced failure regime, the depth of concrete in compression equals 0.617 times the effective section depth. The axial resistance of the reinforced concrete section is the sum of forces in concrete and compression and tension reinforcement, which takes the following form after substituting the expressions for the forces. The moment resistance of the reinforced concrete section includes contributions from the moments produced by the three forces. In the above expressions, the stress in the tension reinforcement equals the design yielding strength of steel. The stress in the compression reinforcement can be equal or smaller than the design yielding strength of steel, depending on the location of the compression reinforcement in the section. The compression failure of a reinforced concrete section represents the loading combinations dominated by the axial force and associated with small eccentricities and large depths of concrete in compression. In this regime, the axial force and the depth of concrete in compression are larger than the balanced failure state values. The neutral axis can be either within the section or outside it. In the first case, the bottom reinforcement is in tension, while in the second case, it is in compression. The stress in the reinforcement is equal or smaller than the design yielding strength of steel. For very large depths of concrete in compression, the cross-section approaches a state of uniform axial compression. Since both top and bottom reinforcement yield, symmetric sections have negligible moment resistance. The point of intersection of the interaction diagram with the N-axis represents the case of pure compression failure, corresponding to crushing of concrete and yielding of steel. In this case, the compression resistance consists of the maximum contributions of concrete and steel in the section. The interaction diagram can be divided into additional regimes based on the modes of section failure described. The tension failure part can be divided into the tension control zone and the transition zone. At section failure in the tension control zone, the strain in the tension steel is much larger than its yielding strength, and the depth of concrete in compression is small. At section failure in the transition zone, the depth of concrete in compression increases, while the strain in the tension steel decreases towards its yielding strength. At section failure in the compression control zone, the strain in the tension steel decreases under the yielding strength. The depth of concrete in compression continues to increase until it reaches the effective depth of the section. At this state, the strain in the tension steel is reduced to zero, and above this point, both top and bottom reinforcement are in compression. And that's it. I hope this was helpful, and I hope you join me for some more reinforced concrete design and see how we delve deeper into the design of columns.